Hello everyone, let's solve some LeetCode today. So today we have LeetCode 76, that is minimum window substring. In this problem we have two strings s and t, and we have to figure out the shortest substring of s that contains all the characters that are present in t. So for example, this is the shortest substring present in this given string, which contains all of the characters a, b, c inside of it. Now as you can see that a, b, c do not have to be in same order. Here we have b first, then we have a, and then we have c. It means the order does not matter as long as these characters exist in this string. Now remember that there are other strings also in which these three characters exist. For example, we have this string a, d, o, b, e, c. Inside of it also we have all the three characters, but we are not actually taking this substring because it is not the shortest. So we have to figure out the shortest substring in which we have all the characters that are present in T. So one way to solve this question is to figure out all of the substrings of the given S string and then check if all the substrings contain this T string or not. So we can use two nested for loops to actually figure out all the substrings, and we will have one more for loop to compare the current substring with the T string characters. So it will be almost order of n to the power 3 time complexity, which is pretty damn bad. So what it means is that we need to do something better. We have to figure out a better solution. So whenever you have strings and we are talking about substrings, we have to go through all the substrings. What can we use? We can always use sliding window technique. So that is exactly what is going to be applicable in this case also. Because we have this linear data structure, we are talking about ranges of elements, that is from L to R, right? It's a range of element, which means it's a substring. So we are talking about substrings, we are talking about linear data structure, and both of these are very big hints for sliding window technique. So that is what we are going to use. So now look, in the question it is already told to us that we need to have each and every character that is present inside of the T inside of this substring S, right? What it means is that if I have A two times, it also means that I need to have A two times in my substring. Now understand that we are supposed to keep track of duplicates also in the T. So if I have something like A, B, C, what it means is that I need two A's inside of any substring that I'm going to select. If I don't have two A's, that substring is not valid. Okay, so that substring will not be an answer. What it means is that I need to keep track of what elements or what characters I have, plus how many times do these characters appear inside of the T. And then I will just keep comparing them here, right? So what it means is that I need a way to store the character and its frequency somehow. And the best data structure to do that is hash map. So I will have something like this. I will have a hash map of T, right? So in the T, I have right now three characters. So I have A, B, and C, and their frequency is just 1, 1, 1 because they are appearing only one time in the T. So I will write 1, 1, and 1. So basically this is what we need. We need these elements these many number of times. So we basically have three conditions that A should be 1, B should be at least once, and C should appear at least once inside of the substring that we are going to choose from this string. So now we also need to keep track of the character that we have gone through in this string also, right? So we will have another hash map also that will keep track of the character that we have gone through in the S string. So we will have a hash map like this. It will contain like just say a few rows. So right now I'm just creating only 3 rows because that will be an easier way to handle things. So this is the hash map for S string. Right now A, B, and C all are 0 because we have not gone through any element in the S string. Now as we will start going through elements in the S string, we will keep on changing these. So assume that this box actually represents a sliding window. So I will have this box here and I will simply write L is equals to here, R will also be here. So right now we will start by increasing the window length. What it means is that I will have A inside of the window. So as soon as I place A in the window, I will increase or update the value of A in the hash map also. So right now I have 0. Now I will have 1 in the hash map. Now as soon as I update the hash map, I need to check if this hash map have all the values that are present inside of this also. So what basically I need to do is I need to go through entire hash map from A to C or to Z, and then I have to check is the value of A is equals to the value of A present in the need array. If the value of B is equals to the value of B present here, if the value of C is equal to value of C here, so that I need to check. And since there are 26 alphabets inside of the English language, it means that our inner loop of comparing these two arrays will be order of 26. So we will compare these two hash maps and we will find out that no, right now we have B is equals to 0, C is equals to 0, but we actually need B is equals to 1 and C is equals to 1, right? So we will not do anything. We will simply take our window and we will simply increase our size. So R will actually shift from A to the next element So R will go from here to the next element D, and our window size will also increase. So D is also now within the window. Now we will again compare these two hash maps. Are these two hash maps equal at this point? Well, since it is a D and D does not actually exist in the T, we don't really care, right? So on comparing the hash map, we will figure out that no, the hash maps are still not same. So we will take the R and we will shift it to the next element, right? So we have O right now. And if I try to take O inside of the substring also, so it will look something like this. Now our window length again has increased. We will again compare these two hash maps. Right now we have O, so we are not actually storing O inside of the hash map. We will end up comparing all these hash map and we will find out that no, the hash maps are still not equal, right? The B is 0, the C is 0, but they need to be 1 and 1 at least, right? So then we will shift the R again, and the R actually points to B now. And then we will simply take the window. So now we have B here, and now we will take the count of B first, and we will increase it to 1, and then we will compare the entire hash map, all the elements in both the hash map again, and we will find out that okay, fine, this condition is true, right? A is equals to 1 in both of these hash maps. Then B is also true, right? B is equals to 1 in both of the hash map, but C is equal to actually 0 in one hash map and it is 1 in another hash map. So this is not true right now. So that means we have still not found a subarray in S that contains all the characters present in the T, right? So we will keep on moving forward. So we will take the R, we will shift it to the next element, that is E, and we will actually increase the size of our window. So now we have E inside of the window also. Since E does not exist in the T, there is no point in adding it in the have array or have hash map and comparing it. But at the end of the day, that's how the code will be. So it will try to compare all these elements again. So the hash maps will be compared again, and we will find out that no, they are not equal. So we will again shift the R to the next one. Then we will get C. Our window size will increase and it will keep or accommodate C also. So now we can actually take the 0 out and we will place 1 here. And now if we compare both of the hash map in the code, we will find out that yes, all of these three conditions are actually true now. So this is also equals. And at this point, we know that we have found a substring that contains all of the characters that are present in T. As you can see that we have A, we have B, and we have C. So all the characters that are present in the T are also present in the particular substring right now. But we are still not sure if it is the shortest, so we still need to do something. First of all, we will take this length. So right now the length is 1, 2, 3, 4, 5, 6. It is 6. So current result is going to be 6. Rest is equals to 6, right? And now we are going to try and find out a substring that is going to have all the elements that are present in T inside of it, but it is going to be less than 6 in length. So to do that, I need to take the window and shrink it. So I will take the A first of all, and I will reduce its count in the hash map. So the 1 will be reduced to 0, and I will shrink the window. So window will actually become something like this. We only have DOBEC in the window now. L will also shift. So L is no longer here. L will be on the D. So L has shifted, the window has decreased, and we have also decreased the count of A. And now we can check the entire hash map again, and we will find out that this condition, we have A is equals to 0 here, and we have A is equals to 1 here. So this condition is actually not true anymore. So it means we are not able to create a shorter string anymore. Now we need to take the window and increase its size to actually move forward for other substrings, right? We need to figure out what are the other substrings that we have. So we have increased the window size. The R will also shift to the next element, that is O, and then we will again check in both of these hash maps. And since O is not actually a part of this T, it will not make much of a difference for us. So both of these hash maps will still be the same. It means this condition is still untrue, and we will have to again increase the size of the window. So we will take the window, we will increase its size again, and we will have D inside of it. Similarly, D is also not part of the T, right? So on comparing the hash maps, we will again get the same state. The A is 0 here, the A is 1 here. So again, the condition is not met. So we will have to increase the window size. So we will take the window, we will increase it even more. We have E now. Similarly, E is also not present inside of the ABC, right? So it will also not make any difference. We will have to compare the hash maps again, but it won't make a difference. Then we will take the substring and we will increase its size again. Now as you can see that we have B here, and we also have B inside of the T, right? So we will take the B and we will increase its count in the have hash map. So right now it was 1, we will make it 2, and we will again compare the entire hash map, and we will check that it is still not okay, because the count of A in the current substring, that is this substring from D to B, is still 0. But we need a count of 1 at least in the substring. So what it means is that even now this condition is not true. It is still false, right? So we will have to again increase the window size. So we will take the window here and we will increase its size to accommodate the next character. And now we have A inside of the string, right? So we will take the R, we will shift it again. So R would actually be on the A at this point. I forgot to shift it here and here, but R will be at A, right? So we will take the A and we will update its frequency inside of the hash map. So right now we have 0 inside of the hash map, and we will simply make it 1 again. And now on comparing the hash map, you will see that we have all the conditions satisfied. We have A is equals to 1, so this condition is also satisfied, right? This is actually equal. And we have B is equals to 2, so this condition is also satisfied. Since it is 1 and we have 2, right? So it means that we have more than what we need, so we are basically fine, okay? And we also have one C in the substring, and here also the count of C is actually 1, so this condition is also fulfilling. It means all the 3 conditions are fine, which means we found a substring, okay? We found another substring that have all the elements or all the characters that are present in the T. Now the size of the substring is going to be what? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the size of the substring is 11, and 11 is actually greater than 6, so we will not actually update the result. 6 is less than 11, so we will keep the 6, okay? This is the shortest substring that we could encounter till now, so we will not take 11, we will keep the 6. But now that we have a substring that contains all the elements that are present in the T, we need to find out, is there a smaller substring? So what we will do is we will start decreasing the length of the substring from left side. So we will take the L, we will decrease it, and the window size will become less. So window size will be here. So we remove the D and we will again check, are the hash maps fine? Well, they are still fine because the D was never present in the T, so we did not actually make any difference. Then we will try to again shorten this length. Now remember that as soon as we remove the D, the length will become actually 10. It is smaller than the 11, right? But it is still not smaller than 6, so we will not actually update the result. So we will keep on decreasing the length as much as we can. So we will have the window, we will decrease it again. Since O is also not present inside of the T, the hash maps will be fine. We will again compare both of the hash maps, they will be fine. It means the size actually increased from 10 to 9, right? So we will write 9 here. 9 is again greater than 6, so we will not update the result, but we will keep on decreasing the size of the window. So we have B here, and we will first of all decrease the count of B. So we have 2 here, we will decrease it by 1, and now we will have 1 here. So we have 1 count of B right now. We are going to remove the B from the window, and now we are going to check again the hash maps. Since we only decreased the count of B by 1, we still have a count of 1B inside of the substring, right? And that is also what we need, right? We need 1B and we still have 1B. So this is currently a valid string. This substring still contains all the characters that are present in the T. So it's a valid substring. So currently the length of the substring is 8, right? Because we decreased it by 1. So 8 is still greater than 6. Nothing can be done, right? Now we will take the window and we will decrease it again. So the E will be gone. And since E was not actually present in the T, it does not matter. The hash maps are going to be the same. The substring is still going to be valid. The only thing that will change is that this 8 will actually become 7. So we have a length of 7 now, and 7 is still greater than 6, so we cannot really update the result variable till now. So now we have C here, and we have C also in the hash map, so we will take the value in the hash map for C and we will reduce it by 1. So currently it is 1, right? We will reduce it by 1 and we will get 0. So right now this particular condition is not true, right? And it means that the current decreased substring or the current length of the substring is not valid, right? Because we do not have C in the substring. So it means I need to start increasing the length of the window again. So I will take the length of the window from here and I will increase it by 1. So the R will also increase by 1, right? R will be on N. And since N does not matter because it does not exist in the T, we will compare the hash maps and we will find out that this condition is still not true. C is 0 here, C is 1 here. So this particular substring is still not valid, right? And I forgot to actually place L here, right? So L will actually be right here on the O. L will also keep on, increasing. Now since it is not a valid substring, we will take the length and we will increase it by 1. So now we have C also in the substring. We will update its count in the hash map. So we will take the 0 out and we will add 1 here. And now this condition is also again true, right? So it is true. We will compare the hash maps and we will find out that all the conditions are true. It means we again found a substring that contains all of the characters that are present in the T string also. So right now the length of this substring is actually 7, right? And 7 is greater than 6, so we cannot really update this result variable right now, but we can try to actually decrease the length of this window again. So we have this window and we will simply decrease the length of it. So right now we have O. We will try to remove the O from the hash map, but it does not exist, right? So we will not be able to do anything. We will simply take the window and decrease it by 1. The L will also change from here to here, and now we will actually check our hash map again. Since our hash maps are still fine, right? Nothing has decreased. It means that this current substring, the length is going to be 6. It is still valid. This is valid, right? Now we will try to make it even shorter. So we will take the window again. We will shorten it again. We will remove the d from the hash map. We will compare both of these hash maps again. And we will find out that all of the values in the hash maps are just fine. Which means right now the length is going to be 5. Okay, and 5 is not greater than 6. So we will update the variable result from 6 to 5. So result actually equals to 5 now. And now we will try to go even shorter. We will take the window length, okay, and we will make it even shorter. We remove the e, we again check the hash map. Since both of these hash maps are again equal, it means that this particular substring b, a and c, this is also valid, right? And the length of the substring is actually 4, right? And 4 is less than 5, so we will actually end up updating the result variable from 5 to 4. And now if I try to reduce the size of the window again, we see that we have removed a b. So the count of b will actually decrease in the hash map also, and we will have 0. And now if we try to compare both of these hash maps again, we get that, okay, this condition is not true. We will try to increase the size of the window, but we will not be able to increase it. Why? Because there are no more elements outside of it now. So it means that this is the time when our loop will actually end and we will get the result answer. So this 4 is the result. And now understand that we are actually storing the length of the result, right? But we actually need to store the starting and the ending position. Why? Because we need to return the substring itself, not just the length. So what it means is that we will have another variable also. So we will have something like res range, and it will actually be an array in which we will store the L pointer and the R pointer that we will be having whenever we will actually update this result variable. So whenever you update the result variable, take the values of this current L and current R and then just update this result R variable to make sure that you know the starting and the ending position of the string that you actually consider to be result. So in this solution, the time complexity will actually be order of n multiplied by 26. Okay. The reason we have 26 is because there are 26 alphabets inside of the English language, right? And at the worst case, this entire hash map can be as big as 26 characters, right? So basically, each time we compare these two hash maps, we will have to run a loop of length 26. So that's why we are multiplying 26 with n. The order of n comes from the sliding window technique. So sliding window technique solves everything in order of n. But since at each iteration we are also running this comparison, we end up getting this order of 26. But the question is, can you do better? Can you somehow remove this order of 26 from the time complexity? And the answer is yes. Yes, you can actually do that. Notice that we need to compare these two hash map only to check these conditions. Is A is equal to 1 in this map and it is also equal to 1 in this map? Is B is equal to 1 in this map and it is also equal to 1 in this map? And is C is equal to 1 in this map and it is also equal to 1 in this map? So these are basically three conditions that we are checking, right? And in order to check these three conditions, we actually go through the entire hash maps again and again. But just think about it. Initially the A will be 0, right? And as soon as A becomes 1, we know that one condition has been fulfilled, right? So what I can do is I can just say that, okay, I have a variable have, and have will actually store the number of conditions that we have fulfilled. So I will simply increase have by 1. So right now have will have 1 as a value, right? What it means is that out of these three conditions, 1 has been fulfilled. Now as soon as the B actually becomes 1, instead of 0, it becomes 1, we can actually take the have and plus 1 is. So the value here will become 2. It means two conditions have been fulfilled or completed, right? In the same way, as soon as C becomes 1, or basically it becomes equal to this value, we can see that this third condition is also fulfilled. So we will add 1 also here and we will see, okay, the three conditions have been fulfilled, right? And these three conditions are basically equal to the length of this particular hash map. Is it not true? It is true, right? Because we take all the unique characters that are present in the T, we use them as keys, right? They are the keys and their frequency, the number of times they appear is simply the value, right? So basically the number of unique characters are going to be the conditions. So you can have another variable that is need, and need will contain the total number of conditions that needs to be fulfilled. So here the need will be the length of this hash map, that is going to be 3, and we have to make sure that this have hash map actually fulfills 3 conditions for any substring to be a valid substring. So the benefit that we get from these two variables have and need is that as soon as we get any element, okay, we get A, okay, and it becomes equal to the element here, we just update the have variable. We don't have to go ahead and check the entire hash map again, because if after updating we see that the have value actually is equal to 3, which is equal to the same value as need, we know that we have found the valid substring and we can now start decreasing the window. We don't have to go through the entire hash map. We can just use this have variable and this need variable to determine that, and then we will keep on decreasing the window size until one of these elements, okay, one of these values actually become less than these values. So suppose that c becomes 0, right, and it became less than the proper value. What it means is that we will take the have, okay, and we will decrease it by 1. So it will actually become 2, and as soon as have becomes 2, okay, it became 2, we will stop decreasing the window, we will start increasing the window again. So what happened is that now you are just doing two operations. First of all, you are just checking, is this equal? Are these elements, the current element that we are updating, is its value same as here? If it is not, or if it is, we will just update the have, and then we will take the have variable, and then we will take the need variable, and then just make a comparison between these two. So basically we replace the entire hash map comparison with just two operations, comparing these two variables and comparing these two. And this will actually remove the inner loop of 26. It means the time complexity will now be only order of n, which is a much better improvement. So now that we understand the theory, we can go ahead and look at the code. So here is the code. The first thing that we are checking is the condition on t. So if there is no t, okay, if t is empty or if it is null, then we will simply return empty string, because we don't have any characters to compare to, right? Then here we are creating the count of t. We are taking the t string and we are using the counter function from the Python library to actually create a frequency map. It is just creating the same need map that we had in the drawing explanation. So this is the map for t string, okay? Then here is the window. This is the hash map for the s string. Okay, we are going to store the current substrings values inside of this window hash map. And then we have these two variables, have and need. Have is going to start from 0. Need is going to be the length of the count t. Then we have the result variable and we have result length variable. Result variable contains the starting and the ending position of the string. That's why we have this array here. This represents the starting position, this represents the ending position. And result length represents the length of the string. So we are storing this infinity inside of it because we need to minimize it, and in order to minimize something we first of all start from the maximum value that we can find. Then we have the left pointer to 0, and now we have the right pointer inside of this for loop. So now we are going from 0 to the end of the string with the help of this r pointer in this for loop. So first of all, here we are taking access to the character c from the s string, and then we are incrementing its value in the window hash map. Now what this line of code does is that if there is some value for this particular character in the window hash map, we will get that value, otherwise we will get 0, and whatever we get we will add 1 into it, and we will store this entire value inside of the window c place. Now that we have updated the count of character c in window hash map, we will check if this character actually is present in the count t. What it means is that is this character c is actually part of the t string. If it is present, then we check is the value for the character c in window hash map is same as the value for character t in a count t hash map. We can increase the have by 1. So that's what we are doing here, okay? And then here we are checking while have is equal to the need. What this condition means is that we have found a valid substring that contains all the characters from t inside of it, right? So while we have a valid substring, that is while we have double is equal to need, we can try to decrease the size of the window. So that's what we are doing here. First of all, we are taking the length of the current substring. If it is less than the result length, we can update the result variable, okay? So the new L and new R pointer will be stored for the result variable, and the new result length will be stored here. Now here we will have the character at L pointer. We will have its value in the window hash map, and we will decrement it, decrease it by 1. And then here we are checking if the character at L index is actually present in the count t. If it is present, then we check if the character at L index x value in the window hash map is less than x value in the count t hash map. Then we know that we are not fulfilling one of the conditions for a character. So we will simply decrement have by 1. And then we will simply increment L by 1. The reason we are incrementing L by 1 is to actually reduce the window size. So if you increment R by 1, it will increase the window size. If you increment L by 1, it will decrease the window size by 1. And once this entire for loop runs, we will have our result. So right here on line 34, we are taking the values from the result and we are setting as the new value for L pointer and R pointer here. And here in the return statement, we are simply returning the substring from L to R plus 1. R plus 1 simply because R plus 1 is not inclusive. So everything till R will be inclusive and R plus 1 will be left out. So that's why we have S from L to R plus 1. So this is the substring that we can return. And we will only return the substring if the result length is actually not infinity. Okay, if the result length has changed somehow, then only we will actually return this thing. Otherwise, we will return the empty string. Result length will stay infinity in case there is some character missing in the S string that is actually present in the T string, which means we will never actually get a string or substring in the S that will have all the characters present in the T, and in that case, the result length will never actually update and it will keep staying infinity forever. So now let us start to run this thing and see what happens. So yeah, our solution runs in 67 milliseconds, beats 70.75% solutions on LeetCode, and it passes all the 268 test cases. Our solution is pretty efficient. Now let us look at the time and space complexity for this particular solution. So the time complexity is very simple. It is going to be order of n, or it is going to be order of 26 multiplied by n in case you do not use that optimization for removing the comparison between hash maps. The space complexity is constant, but then you will say that Satyam, why is it constant? I mean, we are actually allocating two hash maps for these two strings s and t, right? Well, it is constant because those two hash maps can only be length 26. The maximum number of elements that you can store in any hash map is going to be 26 because there are only 26 characters inside of the English alphabets, right? There is no other character. What it means that the string S and T are going to only have 26 unique characters. That's why we will only have 26 characters in both of these hash maps. So that's why it will actually become order of 52, right? And which is basically order of 1 because it is constant. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.